Conditional Generative Adversarial Nets. Authors: Mehdi Mirza from University of Montreal, Simon Osinduro from Flickr and Yahoo. Abstract: Generative adversarial nets were recently introduced as a novel way to train generative models. In this work, we introduced the conditional version of generative adversarial nets, which can be constructed by simply feeding the data we wish to condition on to both the generator and discriminator. We show that this model can generate MNIST digits conditioned on class labels. We also illustrate how this model could be used to learn a multi-modal model, and provide preliminary examples of an application to image tagging. In this example, we demonstrate how this approach can generate descriptive tags which are not part of training labels. 1. Introduction. Generative adversarial nets were recently introduced as an alternative framework for training generative models in order to sidestep the difficulty of approximating many intractable probabilistic computations. Adversarial nets have the advantages that Markov chains are never needed. Only backpropagation is used to obtain gradients, no inference is required during learning, and a wide variety of factors and interactions can easily be incorporated into the model. Furthermore, as demonstrated in the cited work, it can produce state-of-the-art log likelihood estimates and realistic samples. In an unconditioned generative model, there is no control on modes of the data being generated. However, by conditioning the model on additional information, it is possible to direct the data generation process. Such conditioning could be based on class labels, on some part of data for inpainting, or even on data from a different modality. In this work, we show how we can construct the conditional adversarial net. For empirical results, we demonstrate two sets of experiments, one on MNIST digit data set conditioned on class labels, and one on the MIR Flickr 25,000 dataset for multi-modal learning. 2. Related work. 2.1 Multi-modal learning for image labeling. Despite the many recent successes of supervised neural networks, and convolutional networks in particular, it remains challenging to scale such models to accommodate an extremely large number of predicted output categories. A second issue is that much of the work to date has focused on learning one-to-one mappings from input to output. However, many interesting problems are more naturally thought of as a probabilistic one-to-many mapping. For instance, in the case of image labeling, there may be many different tags that could be appropriately applied to a given image, and different human annotators may use different, but typically synonymous or related, terms to describe the same image. One way to help address the first issue is to leverage additional information from other modalities. For instance, by using natural language corpora to learn a vector representation for labels in which geometric relations are semantically meaningful. When making predictions in such spaces, we benefit from the fact that when prediction errors occur, we are still often close to the truth, such as predicting table instead of chair. Additionally, we can naturally make predictive generalizations to labels that were not seen during training time. Works have shown that even a simple linear mapping from image feature space to word representation space can yield improved classification performance. One way to address the second problem is to use a conditional probabilistic generative model. The input is taken to be the conditioning variable, and the one-to-many mapping is instantiated as a conditional predictive distribution. A similar approach to this problem is taken in the cited work, where a multimodal deep Boltzmann machine is trained on the MIR Flickr 25,000 dataset. Additionally, another work shows how to train a supervised multimodal neural language model that is able to generate descriptive sentences for images. 3. Conditional adversarial nets. 3.1 Generative adversarial nets. Generative adversarial nets were recently introduced as a novel way to train a generative model. They consist of two adversarial models, a generative model G that captures the data distribution, and a discriminative model D that estimates the probability that a sample came from the training data rather than GE. Both G and D could be a non-linear mapping function, such as a multi-layer perceptron. To learn a generator distribution over data, the generator builds a mapping function from a prior noise distribution to data space. The discriminator outputs a single scalar representing the probability that the data came from training data rather than the generator's output. G and D are both trained simultaneously, Parameters for G are adjusted to minimize the logarithm of 1 minus the discriminator's output of the generator's sample, and parameters for D are adjusted to minimize the logarithm of the discriminator's output for the real data. This training follows a two-player min-max game with the value function. Minimize with respect to G, and maximize with respect to D, the value function. 3.2. Conditional Adversarial Nets. Generative adversarial nets can be extended to a conditional model if both the generator and discriminator are conditioned on some extra information. This information could be any kind of auxiliary data, such as class labels or data from other modalities. We can perform the conditioning by feeding this auxiliary data into both the discriminator and generator as an additional input layer. In the generator, the prior input noise and the auxiliary data are combined in a joint hidden representation. The adversarial training framework allows for considerable flexibility in how this hidden representation is composed. In the discriminator, the real or generated data and the auxiliary data are presented as inputs to a discriminative function. The objective function of this two-player min-max game is minimize with respect to G and maximize with respect to D, the value function. Figure 1 illustrates the structure of a simple conditional adversarial net. 4 experimental results. 4.1. On a model. We trained a conditional adversarial net on MNIST images conditioned on their class labels, encoded as one-hot vectors. In the generator net, a noise prior with dimensionality of 100 was drawn from a uniform distribution within the unit hypercube. Both the noise and the labels are mapped to hidden layers with rectified linear unit activation, with layer sizes of 200 and 1000 respectively, before both being mapped to a second, combined hidden layer with a dimensionality of 1200. We then have a final sigmoid unit layer as our output for generating the 784-dimensional MNIST samples. In the discriminator, the MNIST images are mapped to a max-out layer with 240 units and 5 pieces, and the labels are mapped to a max-out layer with 50 units and 5 pieces. Both hidden layers are then mapped to a joint max-out layer with 240 units and 4 pieces, before being fed to the sigmoid layer. The precise architecture of the discriminator is not critical as long as it has sufficient power. We have found that max-out units are typically well suited to the task. The model was trained using stochastic gradient descent with mini batches of size 100 and initial learning rate of 0.1. which was exponentially decreased down to 1/1,000,000th with a decay factor of 1.00004. Also, momentum was used with an initial value of 0.5, which was increased up to 0.7. Dropout with a probability of 0.5 was applied to both the generator and discriminator. The best estimate of log likelihood on the validation set was used as the stopping point. Table 1 shows Gaussian Parson window log likelihood estimates for the MNIST dataset test data.war. 1,000 samples were drawn from each of the 10 classes, and a Gaussian Parson window was fitted to these samples. We then estimated the log likelihood of the test set using the Parson window distribution. The conditional adversarial net results that we present are comparable with some other network-based results, but are outperformed by several other approaches, including non-conditional adversarial nets. We present these results more as a proof of concept than as a demonstration of efficacy, and believe that with further exploration of hyperparameter space and architecture, the conditional model should match or exceed the non-conditional results. Figure 2 shows some of the generated samples. Each row is conditioned on one label, and each column is a different generated sample. 4.2. Multi-modal. Photo sites such as Flickr are a rich source of labeled data in the form of images and their associated user-generated metadata. In particular, user tags. User-generated metadata differ from more canonical image labeling schemes in that they are typically more descriptive, and are semantically much closer to how humans describe images with natural language rather than just identifying the objects present in an image. Another aspect of user-generated metadata is that synonyms are prevalent and different users may use different vocabulary to describe the same concepts. Consequently, having an efficient way to normalize these labels becomes important. Conceptual word embeddings can be very useful here, since related concepts end up being represented by similar vectors. In this section, We demonstrate automated tagging of images with multi-label predictions using conditional adversarial nets to generate a possibly multi-modal distribution of tag vectors conditional on image features. For image features, we pre-train a convolutional model similar to a well-known model on the full ImageNet dataset with 21,000 labels. We use the output of the last fully connected layer with 4,096 units as image representations. For the word representation, we first gather a corpus of text from a concatenation of user tags, titles, and descriptions from the Yahoo Flickr Creative Commons 100dm dataset metadata. After pre-processing and cleaning the text, we train a skipgram model with word vector size of 200. We omit any word appearing less than 200 times from the vocabulary, thereby ending up with a dictionary of size 247,465. We keep the convolutional model and the language model fixed during the training of the adversarial net. We leave the experiments where we backpropagate through these models as future work. For our experiments, we use the MIR Flickr 25,000 dataset and extract the image and tags features using the convolutional model and language model we described above. Images without any tags were omitted from our experiments, and annotations were treated as extra tags. The first 150,000 examples were used as a training set. Images with multiple tags were repeated inside the training set once for each associated tag. For evaluation, we generate 100 samples for each image and find the top 20 closest words using cosine similarity of vector representation of the words in the vocabulary to each sample. Then we select the top 10 most common words among all 100 samples. Table 2 shows some samples of the user-assigned tags and annotations along with the generated tags. The best working models generator receives Gaussian noise of size 100 as a noise prior and maps it to a 500-dimension ReLU layer. It maps the 4,096-dimension image feature vector to a 2,000-dimension ReLU hidden layer. Both of these layers are mapped to a joint representation of a 200-dimension linear layer, which outputs the generated word vectors. The discriminator consists of 500 and 1,200 dimension ReLU hidden layers for word vectors and image features respectively, and an X-out layer with 1,000 units and 3 pieces as the joint layer which is finally fed to one single sigmoid unit. The model was trained using stochastic gradient descent with mini batches of size 100 and initial learning rate of 0.1, which was exponentially decreased down to 1 millionth with a decay factor of 1.0004. Also, momentum was used with an initial value of 0.5, which was increased up to 0.7. Dropout with a probability of 0.5 was applied to both the generator and discriminator. The hyperparameters and architectural choices were obtained by cross-validation and a mix of random grid search and manual selection, albeit over a somewhat limited search space. 5. Future work. The results shown in this paper are extremely preliminary, but they demonstrate the potential of conditional adversarial nets and show promise for interesting and useful applications. In future explorations, we expect to present more sophisticated models, as well as a more detailed and thorough analysis of their performance and characteristics. User tags and annotations include Montana, Trem, Inverno, Frio, people, male, plant life, tree, structures, transport, car, white car. Generated tags include taxi, passenger, line, transportation, railway station, passengers, railways, signals, rail, and rails. User tags and annotations include food, raspberry, delicious, homemade. Generated tags include chicken, fattening, cooked, peanut, cream, cookie, house-made, bread, biscuit, and bakes. User tags and annotations include water, river, tow. Generated tags include creek, lake, along, near, river, rocky, tree line, valley, woods, and waters. User tags and annotations include people, portrait, female, baby, indoor. Generated tags include love, people, posing, girl, young, strangers, pretty, women, happy, and life. Also, in the current experiments, we only use each tag individually, but by using multiple tags at the same time, effectively posing the generative problem as one of set generation, we hope to achieve better results. Another obvious direction left for future work is to construct a joint training scheme to learn the language model. Work has shown that we can learn a language model suited for the specific task. Acknowledgements. This project was developed in the PyLearn2 framework, and we would like to thank the PyLearn2 developers. We also like to thank Ian Goodfellow for helpful discussions during his affiliation at the University of Montreal. The authors gratefully acknowledge the support from the Vision and Machine Learning, .GUT, and production engineering teams at Flickr. The teams include Andrew Stadlin, Ariel Cordero, Clayton Molina, Cyprian Noel, Frank Liu, Gary Pesavento, Hui Nguyen, Jack Culpepper, John Coe, Pierre Garrigues, Rob Hess, Stacy Svetlichnaya, Toby Baumgartner, and Yi Lu.